Let's talk about one of the absolute biggest questions in all of science. Why is our universe even here? Seriously, it's a cosmic mystery story that involves a missing twin, a high-stakes competition at the very dawn of time, and, well, a completely new way of looking at reality itself.
This might sound like a late-night philosophical question, but it's actually a massive physics problem. See, the Big Bang should have cooked up equal amounts of two things. Matter, that's the stuff that makes up you, me, the stars, everything, and its counterpart, antimatter. But if that had happened, they would have instantly found each other, annihilated in a gigantic flash of pure energy, and left behind, well, nothing, an empty universe filled with just light. The fact that we're here to even ask this question is the real mystery.
So here's the puzzle. On one side, you've got matter. It's solid, it's everywhere, it's the universe we know and love. And on the other side, you've got its missing twin, antimatter, which has basically vanished. To figure this out, we first have to ask, what even is antimatter really?
Yeah, the answer might be a whole lot simpler, and honestly, more elegant than what you might think. Let's start by just clearing up a few common ideas, mostly thanks to science fiction.
We've all seen it in the movies, right? Antimatter is this super exotic, incredibly rare substance. It's negative matter from some mirror universe, or maybe it's the perfect opposite of normal stuff, used to power starships or make city-leveling bombs. And while that's awesome for telling a good story, thinking about it that way might actually be hiding what's really going on.
What if the answer isn't about two totally different types of stuff at war with each other? What if it all just comes down to waves? There's a new model that suggests exactly that, and it gives us a fresh and, frankly, a much more beautiful way to look at the problem.
Okay, it's called the Harmonic Scale Framework, or HSF. Now, don't worry, we're not going to get bogged down in the deep math here. The main idea is actually really simple. Imagine the whole universe is just made of waves. And the things we call particles, electrons, protons, all that, they're just stable points where these waves are vibrating, kind of like a perfect clear note humming on a guitar string.
And this is where the whole mystery begins to unlock. In this wave-based picture, antimatter isn't a separate thing at all. It is the exact same fundamental wave as matter. The only difference is that it starts from a different point in its cycle. Think of it like this. It's not a different song. It's the same song, just starting on a different beat. Physicists call this a phase shift. And this chart just makes it crystal clear. I mean, look at everything they have in common. According to this model, they've got the same mass, same inertia. They react to gravity the same way. They are both just stable little pockets of energy. They're practically identical twins. The only thing that's different, the one thing that gives them their identity, is that their internal waves are just out of sync with each other.
So okay, if the only difference is this little wave phase, how did one end up totally dominating the other one? To answer that, we have to rewind the clock way, way back to the first fraction of a second after the Big Bang. This is where the fate of everything was decided in a kind of cosmic contest.
All right, so picture it. The Big Bang happens, and boom, just like standard physics tells us, equal amounts of matter and antimatter pop into existence. But the universe they were born into was just unbelievably chaotic, a turbulent, warped, seething soup of pure energy. And this crazy environment set the stage for what we call the Great Annihilation, where almost everything was about to get completely wiped out. Imagine every single one of these brand new particles getting blasted by a fire hose of energy from the universe itself. And it wasn't a nice, even flow. It was a violent, chaotic flood of energy being pumped right into their cores. And how each of them handled this flood, well, that was literally the difference between life and death. Which brings us right back to the central question. If they're nearly identical twins in every important way, how did one wave configuration, the one we call matter, manage to survive this chaos, while its twin, antimatter, just perished?
Well, the answer wasn't a battle of strength or power. It all came down to a simple wave trick, a tiny, subtle advantage in what was basically a cosmic stability contest. Okay, so here's the trick. When all that crazy energy came flooding in, both wave configurations tried to absorb it. But the one we call matter had a structure that was really good at holding on to that energy efficiently. The antimatter configuration, on the other hand, it was leaky. It just couldn't stabilize that incoming energy fast enough. It was kind of like trying to fill a bucket with a massive hole in the bottom. It just collapses and disappears. So you see, the universe didn't choose matter.
It didn't have a favorite. It was just a simple question of physics. The matter configuration just happened to have the wave structure that was a little more stable, a little more efficient in those extreme conditions. It basically won by default.
And the scale of this tiny little efficiency advantage, well, that is what's truly mind-blowing. This tiny, subtle difference is the single reason why we and everything we see exist at all.
So just how small was this advantage? It was 1 part in a billion. That's it. An almost unthinkably tiny difference in how well one of these wave configurations could hold on to energy compared to the other. But when you're dealing with the massive numbers of the early universe, a tiny fraction like that changes everything. So here's what that number really means. During that great annihilation, for every 1 billion antimatter particles that failed the stability test and vanished, and for the 999,999,999 matter particles that vanished right along with them, just one, a single matter particle, managed to hold on and survive.
This chart just shows it perfectly. You start with this enormous ocean of particles, over 1 billion of them for every one that would eventually survive. The vast, vast majority just cancel each other out. But because of that tiny 1 in a billion advantage, this tiny sliver is left over. And that tiny leftover bit, that cosmic rounding error, well, that became everything. Every star, every planet, every galaxy.
So let's just bring it all home. Why is the universe made of matter? Because matter and antimatter aren't really different substances, they're just different wave configurations. And in the chaotic first moments of the universe, one of those configurations was just a tiny bit more stable. That tiny advantage allowed an incredibly small fraction of matter to survive the annihilation, and that surviving fraction is what we now call our universe.
Ultimately, what this whole model is suggesting is pretty profound. It says that one of the biggest, deepest mysteries in all of cosmology, the reason for our very existence, just boils down to something as simple and as elegant as a phase relationship between 2 waves.
And that kind of leaves us with one last really big thought. If a simple shift in a wave's rhythm is enough to create an entire cosmos out of total annihilation, what other secrets of the universe are just hiding in plain sight, waiting to be explained not by some exotic new particle, but by the simple, beautiful language of waves?